Dear students, welcome to the next lecture of electrochemistry. In the last lecture, we have discussed what is electrode potential, the different two main types of electrode potentials, that is oxidation potential and reduction potential. We have also discussed standard electrode potential according to IUPAC conventions. We have seen Nernst equation. We have derived Nernst equation in the last lecture, and we have determined the cell potential of different types of cells also. Now, today we will be, and we have also discussed the relation between the cell potential and gift free energy in the last lecture. So today we'll discuss the relationship between standard cell potential and equilibrium constant of the cell reaction. Relation between standard cell potential and equilibrium constant of the cell reaction. For any galvanic cell, the overall reaction at equilibrium can be represented as follows. In a galvanic cell, the reactants are converted into product, and the product can again be converted into reactant. It is a reversible reaction. So for example, let us try to take an example of a Daniell cell. In this Daniell cell, zinc reacts with copper to form ionic zinc and copper solid. In the reverse reaction, this copper, it releases electrons and it forms Cu++. So in this equilibrium, the equilibrium constant for this reversible reaction can be obtained by K, which is called as the equilibrium constant, is equal to molar concentration of product upon the molar concentration of the reactant. For example, the equilibrium constant for Daniell cell is equal to K is equal to molar concentration of ions, only ions of the product, that is zinc, upon the molar concentration of the reactant, that is Cu++. So the equilibrium constant is related to the standard free energy change. Standard free energy change as follows. We all know this equation. So free energy change is equal to RT log natural K. RT into log natural K. As we all know that K is called as the equilibrium constant. So the standard cell potential, if E cell is the standard cell potential or EMF of a standard cell of a galvanic cell, then therefore we can write this equation of standard free energy change as standard free energy change is equal to minus N into F into E standard cell. Standard free energy is equal to minus N into F into E standard cell. So when we compare these two cells, the free energy change, standard free energy change of these two, and we write a new equation. By comparing these above equations, we can write a new equation that free energy is equal to free energy is equal to free energy is equal to free energy. So NF into standard cell is equal to RT log natural K is equal to RT log natural K. Therefore, we write E standard cell, the value of standard cell potential can be calculated is equal to RT upon NF into log natural K. This is the relationship, or we call it as the relationship between standard cell potential and equilibrium constant for a cell reaction. For a cell reaction, or the E standard cell is equal to 2.303. As we all know that we can use uh, at constant temperature, at definite temperature, 2.303. If you want to remove this log natural, we can use log with the base 10 by adding 2.303. So E standard cell is equal to 2.303 into RT upon NF into log with the base 10 K, that is equilibrium constant. So is if the temperature is 25 degrees Celsius, or which is equal to 298 Kelvin, then we can write this above equation as 2.303 R into T upon F is equal to 2.303 is equal to 2.303 plus we know the value of R, that is 8.314, into the temperature, that is 298 Kelvin, upon the value of Faraday, that is 96500. So when we calculate these substituted values, the answer comes to be 0.592. Answer comes to be 0.592. So therefore, we substitute this answer. So E standard cell, the standard cell potential is equal to 0.592 into R into T upon N into F into log with the base 10K. Log with the base 10K. So this is called the relation between equilibrium constant and the standard cell potential So a very important point from the view of examination. Now let us go on to the next point, which is called as standard hydrogen electrode. Standard hydrogen electrode. As you all know, that there are the electrode potential of a single electrode cannot be measured. So the cell potential can be measured experimentally. So it is necessary to have some electrode which is called as a reference electrode. So this standard hydrogen electrode is a primary reference electrode. Reference, you know the meaning of reference. Uh, uh, Pre-known thing is called as a reference. So standard hydrogen electrode is called as a reference electrode. Look at this diagram. This is the diagram of a standard hydrogen electrode. So let us discuss the construction of this standard hydrogen electrode. So this standard hydrogen electrode consists of a platinum plate. So this is a platinized platinum plate which is coated with platinum black, and this platinum plate is connected to copper wire. It is connected to external circuit by using copper wire. There is a narrow glass tube outside this copper wire. There is a narrow glass tube. At the bottom of this narrow glass tube, there is a mercury. There is a mercury. So this platinum electrode is dipped. This platinum electrode is dipped in 1 molar H plus ion solution. The solution is kept saturated, or the solution is kept dissolved by bubbling pure and dry hydrogen gas at 1 atmosphere. At 1 atmosphere. So through the outer jacket, we can pump in the pure and dry hydrogen gas at 1 atmosphere pressure and at 298 Kelvin. So this platinum plate plays a very important role. It does not take part in the electrode reaction, and uh, as it is a inert, platinum is an inert element. So this inert electrode serves as a site for transfer of electrons. Transfer of electrons. So in this way, this is called as a construction of standard hydrogen electrode. So again, I repeat again, it is a primary reference electrode. This primary reference electrode consists of a beaker, and in this beaker, the complete uh, glass vessel is placed. There is an inner jacket, there is an outer jacket. From the outer jacket, hydrogen gas is pumped in, and the inner jacket has a platinum wire. And at the bottom of the platinum wire, there is mercury, and this platinum wire, at the end, there is a platinum plate, and this platinum plate is coated with platinized platinum black. So now let us go on to the drawbacks of or working of what is called as standard hydrogen electrode. So the standard hydrogen electrode can be represented as, so H plus ion, its concentration, that is 1 molar, a vertical line. It is in contact with hydrogen gas at 1 atmosphere, a single vertical line, and at the far right hand side, there is a platinum. There is a platinum electrode. So the reactions taking place, the working of the standard hydrogen electrode is as follows. So these H plus ions, they accept the electron. They accept the electron and they give half hydrogen, half H2, and the potential developed, and the standard potential developed is 0.0 volt. 0.0 volt. So, as you all know, that this hydrogen gas is in contact with H plus ions, and when there is equilibrium attained in this reaction, there is a potential developed, and the potential developed is zero potential. The potential developed is zero potential. So this, the applications of standard hydrogen electrode. So this standard hydrogen electrode, it is a reversible galvanic cell with the experimental indicator that it, if it is connected with any other electrode, that is, if, for example, Zn zinc rod dipped in zinc ion solutions, and then its general potential can be calculated as follows. For example, this zinc rod dipped in zinc ion solution and a salt bridge is connected with the standard hydrogen electrode, that is H plus aqueous, 1 molar concentration, H2 gas, 1 atmosphere, and a platinum electrode at the far right hand side. And far left hand side, there's a zinc electrode. When they are connected with each other, the standard potential can be calculated. E cell, the potential of the cell can be calculated. E cell is equal to potential of the standard electrode minus the potential of the this electrode that we are using, that is zinc rod dipped in zinc ion solution. So as we all know that the potential developed on standard hydrogen electrode is zero, so therefore zero minus the potential of the other electrode. So the potential of the other electrode can be directly obtained. So the E cell is equal to minus, E cell is equal to minus E m to the power n plus upon m. So this is called as the potential of the other electrode, which can be directly known. So now let us go on to the disadvantages of the standard hydrogen electrode. So this standard hydrogen electrode has many disadvantages. This standard hydrogen electrode, it is difficult to construct and it is very difficult to handle to a common man who does not know the knowledge of chemistry. A pure and raw hydrogen cannot be supplied continuously to this standard hydrogen electrode. And the pressure of the hydrogen gas, which is to be maintained, that is 1 atmosphere, cannot be maintained, or it is difficult to maintain the pressure that is 1 atmosphere continuously during the working of the electrode. And one more point is that the active masses, the concentrations of the H plus ions in the HCl solution, which is to be maintained 1 molar, cannot be maintained continuously. So these are the disadvantages of standard hydrogen electrode. Now let us go on to the different types of cells, that is, there are which are useful in our day-to-day life. So galvanic cells which are used in our day-to-day life are primary voltaic cell and secondary voltaic cell. They are classified into two main classes, that is primary voltaic cell and secondary voltaic cell. So when a galvanic cell discharges during current generation, during current generation, the chemicals are consumed. Chemicals are consumed in primary voltaic cell. In primary voltaic cell, once the chemicals are completely consumed, the cell reaction stops. The cell reaction stops. The cell reaction cannot be reversed. The cell reaction cannot be reversed even after reversing the direction of the flow of these flow of current, or these cells cannot be recharged. The most familiar example of this type of primary voltaic cell is a dry cell. I repeat again, a very commonly used primary voltaic cell is a Daniell cell, is a dry cell which is commonly used, and in this dry cell uh, there is a current generation, and this current generation is due to consumption of chemicals, is due to consumption of chemicals, and the chemicals are completely consumed. Chemicals are completely consumed, and when there is consumption of chemical, the chemical reaction stops, and the cell reactions cannot be reversed even after the reversion of the flow of direction of flow of current, then the cell cannot be recharged. So such type of cells are called as primary voltaic cell. The dry cell that we commonly used is an example of a primary voltaic cell. The second very important cell that we use in our day-to-day life is called as a secondary voltaic cell. So this secondary voltaic cell, in this the chemicals are consumed. So during current generation, the chemicals are consumed, and these chemicals which are consumed can be regenerated. For this purpose, an external potential which is slightly greater than the cell potential is applied across the electrodes. So this results in reversal of the direction of flow of current, causing the reversal of the cell reaction. Means that cell reactions can be reversed. So this is recharging of the cell. This is called as recharging of the cell. The voltaic cells which can be recharged are called as secondary voltaic cells. And it is very amazing to see that these secondary voltaic cells or galvanic cells during discharge, during discharge, and they are galvanic cells during discharging, and these secondary cells are electrolytic cells during recharging, are electrolytic cells during recharging. The example of secondary cells are lead storage battery, mercury cell, and nickel cadmium cell. I repeat again, These secondary voltaic cells, the commonly used in our day-to-day life is storage battery, mercury cell, and nickel cadmium cell. Now, let us discuss one of the cell, that is nickel cadmium cell. Nickel cadmium cell. This nickel cadmium cell is a secondary dry cell. It is a rechargeable cell and hence it is a reversible cell. It consists of, this nickel cadmium cell consists of a cadmium electrode which is in contact with an alkali. It acts as an anode, while nickel oxide, which has four valencies, that is NiO2, is in contact with the alkali, acts as a cathode. It acts as a cathode. Alkali acts as an anode, and the nickel NiO2 oxide, which is in contact with alkali, acts as a cathode. So the alkali used is moist paste of potassium hydroxide. Alkali used is a moist paste of potassium hydroxide. The reactions that are taking place in this cell are as follows. Oxidation and reduction. Two types of reactions are taking place in NiCad cell or nickel cadmium cell. Here, firstly, the cadmium combines with the alkali, the hydroxide ions of the alkali, and it forms cadmium hydroxide along with the donation of electron. So in this next reaction, that is in reduction, the electrons are accepted. The oxide of nickel, that is NiO2, along with water, reacts with these electrons, and a hydroxide paste, NiOH taken twice, along with hydroxide ions are formed in the reduction. So when we talk about the overall reaction, the combination of these two reactants takes place. So nickel oxide combines with cadmium to form, along with water to form cadmium hydroxide along with nickel hydroxide. Cadmium hydroxide along with nickel hydroxide. So in this overall net reaction, electrodes, only solids are taken into consideration, involve electrolytes, but solids are not involved. The voltage is independent of the concentration of the alkali electrolyte. The voltage obtained during this electrolysis is independent of the concentration of the alkali electrolyte. The cell potential that is developed due to nickel cadmium cell is near about 1.4 volts. The cell has, this nickel cadmium cell has a longer life than any other dry cell. A very important cell which has been used nowadays is called as nickel cadmium cell. Now let us go on to the next type of cell, which is called as hydrogen oxygen cell. Hydrogen oxygen fuel cell. So this hydrogen oxygen fuel cell, hydrogen oxygen fuel cell is very important from the point of view of examination. The functioning of the fuel cell is based upon the combustion reaction. In this, the two gases, that is hydrogen and oxygen, combine with each other to form H2O. So as we all know, the combination of these two gases is an exothermic redox reaction. So this redox reaction can be used to produce electricity. So this common type of hydrogen oxygen fuel cell, in this the reactants of the fuel cell can be continuously supplied from the atmosphere outside, and hence this cell can be used to supply electricity for a very long period. Can be used to supply electricity for a very long period. So with this, we'll stop for today. We'll continue with the electrochemical series in the next lecture. Hey Rohit.